steel, the quintessential material of modern civilization, stands as a testament to human ingenuity and the marvels of engineering and physics interwoven in its creation. Let us embark on a journey through the labyrinth of metallurgy, exploring the intricate dance of atoms and the mighty forces that shape steel into the backbone of our industrial world. At its core, steel is an alloy, a fusion of iron and carbon, with small amounts of other elements added to enhance its properties. This seemingly simple composition belies the complexity of its production and the profound implications it holds for myriad applications. The journey of steel begins in the fiery depths of a blast furnace, where iron ore, limestone, and coke, a derivative of coal, converge in a crucible of intense heat. Here, the alchemy of metallurgy unfolds as temperatures soar to over 1,500 degrees Celsius, melting the iron ore and reducing it to its elemental form. The limestone acts as a flux, binding impurities and allowing them to be skimmed off, while the coke provides the necessary carbon for the alloy. As the molten iron is drawn from the furnace, it undergoes a transformation akin to a symphony of physics, through a process known as basimerization or basic oxygen steelmaking. Impurities such as sulfur, phosphorus, and excess carbon are further purged, leaving behind a molten pool of refined iron, known as hot metal. This molten metal is then carefully alloyed with precise amounts of carbon, typically between 0.2% to 2.1%, depending on the desired properties of the steel. But steel's journey does not end here. It is merely the beginning of a meticulous orchestration of heat treatment, shaping, and manipulation. Through processes like quenching and tempering, the molecular structure of steel is fine-tuned, imparting strength, toughness, and resilience. Imagine the atoms within the steel lattice, dancing to the tune of heat, aligning themselves into intricate patterns that dictate the material's mechanical properties. The physics behind steel's strength lies in its crystalline structure. At the atomic level, iron atoms arrange themselves in a cubic lattice, forming grains that give steel its distinct texture. The alignment of these grains, coupled with the presence of carbon atoms interspersed within, creates barriers that impede the movement of dislocations or tiny defects in the lattice, thereby reinforcing the material against deformation. Moreover, the addition of alloying elements such as manganese, chromium, nickel, and molybdenum introduces further complexity to the steel matrix, enhancing its corrosion resistance, hardness, and machinability. Each element plays a distinct role in the interplay of forces within the steel, influencing its behavior under varying conditions of stress, temperature, and environment. Indeed, the engineering prowess encapsulated within the realm of steel knows no bounds, from the towering skyscrapers that pierce the heavens to the humble bridges that span yawning chasms. Steel stands as a testament to human achievement and the triumph of intellect over adversity. Its versatility knows no bounds, finding application in industries as diverse as automotive, aerospace, construction, and manufacturing. In the crucible of innovation, steel continues to evolve, spurred onward by the relentless quest for perfection. Advanced techniques such as microalloying, powder metallurgy, and thermomechanical processing push the boundaries of what is possible, ushering in a new era of high-performance materials with unparalleled strength-to-weight ratios and unprecedented durability. The engineering and physics behind steel are a tapestry woven from the fabric of human endeavor, a testament to the boundless potential of scientific inquiry and technological innovation. As we stand on the precipice of a new age, let us marvel at the wonders of steel and the infinite possibilities it holds for the future of humanity. At its core, steel embodies the elegant fusion of iron and carbon, two elemental titans whose union transcends mere chemistry to shape the very fabric of our modern world. This marriage of elements, seemingly straightforward in its composition, belies the intricate dance of atoms and the symphony of physics orchestrating its creation. Within the crucible of a blast furnace, where temperatures soar to searing heights, iron ore undergoes a metamorphosis, shedding impurities and embracing carbon's embrace, giving birth to the molten essence of steel. Yet, this transformation is not merely a chemical reaction but a ballet of thermodynamics, where heat and pressure conspire to mold raw materials into a substance of unparalleled strength and resilience. As the molten metal emerges from the fiery depths of the furnace, it enters a realm where engineering meets alchemy, where the laws of physics reign supreme. Through processes like basic oxygen steelmaking and electric arc furnaces, impurities are purged, and alloying elements are introduced, each playing a pivotal role in sculpting steel's properties to meet the demands of its myriad applications. Here, the principles of metallurgy take center stage, as precise control over temperature, composition, and processing techniques determines the final characteristics of the steel, whether it be the hardness of tool steel, the corrosion resistance of stainless steel, or the ductility of structural steel. But the journey of steel does not end with its creation. Rather, it is but a prelude to a saga of engineering marvels and feats of physics. Through processes like hot rolling, cold rolling, and forging, the molten metal is shaped and molded into an array of forms, each with its own unique properties and applications. Here, the principles of mechanics come into play, as forces are applied, and stresses are calculated to ensure that the steel meets the rigorous demands of its intended purpose. In the realm of structural engineering, for instance, steel beams and columns bear the weight of skyscrapers, bridges, and stadiums, their designs meticulously crafted to withstand the forces of gravity, wind, and seismic activity. Furthermore, the properties of steel can be further enhanced through heat treatment to a delicate balance of temperature, time, and quenching medium that alters its microstructure and mechanical properties. Here, the laws of thermodynamics dictate the transformation of austenite into martensite, ferrite, or pearlite, imparting strength, hardness, and toughness to the steel. By harnessing these principles, engineers can tailor steel to meet the exacting requirements of specific applications, whether it be the wear resistance of cutting tools or the fatigue strength of automotive components. The engineering and physics behind steel are a testament to the triumph of human ingenuity and the relentless pursuit of excellence. From its humble origins in the bowels of a blast furnace to its lofty perch atop the skyline of modern civilization, steel stands as a beacon of progress, a monument to the boundless potential of science and technology. In its alloyed embrace, we find strength, resilience, and the promise of a future forged in the fires of innovation. The journey of steel commences amidst the infernal blaze of the blast furnace, a crucible of unparalleled heat and chemical transformation. Within its fiery depths, a delicate dance of elements unfolds, orchestrated by the principles of metallurgy and the immutable laws of physics. Iron ore, the raw material of steelmaking, is fed into the furnace alongside limestone and coke, forming a potent triad of ingredients essential to the alchemical process. As temperatures within the furnace soar to over 1,500 degrees Celsius, the iron ore undergoes a profound metamorphosis, transitioning from solid to molten form. This molten metal, akin to liquid fire, becomes the canvas upon which the artistry of metallurgy is painted. Yet, amidst the seething cauldron of molten iron, impurities lurk, contaminating the purity of the alloy and compromising its mechanical properties. Enter limestone, the unsung hero of the steelmaking process. Acting as a flux, limestone binds with impurities such as silica, sulfur, and phosphorus, forming slag, a molten byproduct that floats atop the surface of the molten iron like a spectral veil. Through the marvels of physics, this slag is skimmed off, carrying with it the unwanted impurities and leaving behind a purified pool of molten iron, ripe for transformation. But what of carbon, the elemental soul of steel? Here, the role of coke, derived from coal, cannot be overstated. As the furnace rages on, coke undergoes a process of pyrolysis, releasing volatile compounds and leaving behind a residue rich in carbon. It is this carbon that infuses the molten iron with strength and resilience, transforming it from mere metal into the alloyed wonder that is steel. The physics behind this alchemical marriage of iron and carbon are as intricate as they are awe-inspiring. At the atomic level, iron atoms arrange themselves in a crystalline lattice, forming grains that lend steel its distinctive structure. With the addition of carbon, these grains become imbued with newfound strength, as the interstitial carbon atoms impede the movement of dislocations within the lattice, reinforcing the material against deformation. In essence, the journey of steel is a testament to the ingenuity of humankind and the boundless potential of scientific inquiry. From the fiery depths of the blast furnace to the towering edifices of modern civilization, steel stands as a monument to the indomitable spirit of progress, forged in the crucible of human endeavor and shaped by the immutable laws of physics. As the molten iron emerges from the blistering confines of the furnace, it embarks on a transformative journey guided by the principles of physics. This journey, reminiscent of a symphony, orchestrates the expulsion of impurities with precision akin to a maestro conducting an ensemble. Within the crucible of bessemerization or basic oxygen steelmaking, the molten metal encounters a meticulous purification process, where impurities such as sulfur, phosphorus, and excess carbon are coerced into separation through the alchemy of heat and chemical reactions. These unwanted elements are compelled to part ways with the molten iron, leaving behind a purer, sincere essence known as hot metal, poised for further refinement. In the sanctum of the steel mill, hot metal assumes the mantle of potentiality, awaiting the deft touch of alloying to imbue it with bespoke properties. Like a sculptor shaping clay, metallurgists carefully introduce precise amounts of carbon into the molten pool, a delicate dance dictated by the desired characteristics of the steel. This infusion of carbon, typically ranging from 0.2% to 2.1%, represents a convergence of engineering and physics, where the interplay of atomic structures and chemical bonds dictates the material's future behavior. It is a symphony of atoms, each note resonating with the promise of strength, resilience, and ductility, harmonizing to create the symphony of steel. Within the crucible, the alloying process heralds a symphony of atomic rearrangement, as carbon atoms intermingle with iron atoms to form a lattice of unparalleled complexity. This lattice, akin to a vast network of interconnected nodes, defines the material's mechanical properties, shaping its response to external forces and environmental conditions. Through the lens of physics, this lattice becomes a battleground where dislocations, tiny defects in the atomic structure, contend against the forces of deformation. The presence of carbon atoms within the lattice serves as sentinels, fortifying the material's defenses against yielding, fracture, and fatigue, forging a steel of unparalleled strength and durability. As the alloying process reaches its crescendo, the steel emerges from the crucible reborn, a testament to the marriage of engineering ingenuity and the laws of physics. It is a material of boundless potential, poised to shape the world around it with its strength, versatility, and resilience. From the soaring skyscrapers that pierce the heavens to the intricate machinery that powers our civilization, steel stands as a testament to human achievement, to a symphony of engineering and physics, echoing across the annals of history. But steel's journey does not culminate with its initial alloying. Rather, it marks the inception of a meticulous orchestration of heat treatment, shaping, and manipulation. In the crucible of the foundry, where temperatures soar to over 1,500 degrees Celsius, the molecular dance of steel begins. Picture the atoms within the steel lattice, their movements akin to a symphony conducted by the flames, aligning themselves into intricate patterns that govern the material's mechanical behavior. This choreography is not haphazard but rather governed by the laws of thermodynamics and kinetics, with each phase transformation and grain boundary migration sculpting the steel's ultimate properties. Through processes like quenching and tempering, the metallurgist assumes the role of an alchemist, fine-tuning the molecular structure of steel to imbue it with strength, toughness, and resilience. Quenching, where the heated steel is rapidly cooled in a bath of oil or water, freezes the atoms in a state of high energy, locking them into a rigid structure known as martensite. However, this newfound strength comes at a cost of brittleness. Enter tempering, a delicate balance of heat and time, where the steel is reheated to a precise temperature, allowing the martensite to transform into a more ductile and resilient structure. This interplay of heating and cooling is not merely a mechanical process but a manifestation of the intricate interplay between thermodynamics, kinetics, and material science. Moreover, the engineering behind steel extends beyond its mere manipulation in the foundry. It permeates every facet of its application, from the towering edifices of architecture to the precision instruments of industry. Consider the construction of a skyscraper, where the structural engineer must navigate the complex interplay of forces of gravity, wind, seismic activity to ensure the integrity of the steel framework. Here, the principles of structural mechanics come into play, with each beam, column, and brace meticulously designed to withstand the myriad stresses imposed upon it. In the realm of automotive engineering, steel assumes a multifaceted role, balancing the conflicting demands of strength, weight, and cost. Advanced high-strength steels, AHSS, push the boundaries of material science, offering unprecedented levels of strength and crashworthiness while maintaining a lightweight profile. Through techniques like hot stamping and tailor blanking, automotive engineers are able to sculpt steel into complex shapes with unparalleled precision, ushering in a new era of safety and performance.